Okay, welcome everyone again to the University of Washington Astrobiology program's fall seminar series. Today's speaker is Professor Dorian Abbot from the University of Chicago. Dorian got his PhD in 2008, is that right? From Harvard, spent a year there as a postdoc, and then went to U Chicago as a T.C. Chamberlain postdoctoral fellow, and after 2 years as a postdoc there, became faculty. And so now he is an assistant professor. So Dorian's going to speak for about 50 minutes or so, then we'll take questions from the audience, both near and far, whoever's in there remote. You can type your questions into the Adobe Connect chat room, and we'll read those to the crowd that's here. And today is a little bit special in that we need to end pretty sharp at 4 because Almar Shield's general exam is immediately following this event in the same room, so I also hope that you all will stay and listen to Almar talk about the runaway greenhouse. Okay, take it away, Dorian.
Okay, thanks for coming. Should I be standing? Oh no, it just rotated. Great. So if you have a question, please interrupt me while I'm going because we might run out of time at the end. I'll try to end early, but feel free to interrupt. So I'm going to be talking about habitable zone, and this is a picture of the habitable zone based on sort of classic casting concept. And so this is different masses of stars, a star-like sun, less massive, and this is distance from the star. And the happy blue area is the habitable zone where you can sustain liquid water at the surface. And at the inner edge of the habitable zone is moist greenhouse or runaway greenhouse, depending. And at the outer edge, you have either CO2 condensation or increase in Rayleigh scattering due to CO2, so that CO2 can no longer cause warming. And the assumption is that anywhere in here, if you move the planet out further from the sun and it wants to cool down, that the CO2 will adjust to the silicate-weathering feedback, continental feedback, and get as high as it needs to be to keep you in the habitable zone. So that's the assumption. And that's important because if you don't include that geochemical feedback, and so it's not included in this early paper by Hart, what you find is a habitable zone. If you don't include that feedback, but you do include the positive feedbacks of ice albedo and moisture greenhouse feedback, just an increase in moisture and more greenhouse, you get a habitable zone that's something like maybe 0.05 to 0.1 AUs. So it's something like an order of magnitude smaller, 10 times smaller. So this wide habitable zone depends on silicate-weathering feedback. And what I'm interested in, and what I'm going to talk about today, is what if you start changing the land fraction of the planet? What can we say, just in general terms, about what that's going to do to the habitable zone? And there are a lot of uncertainties and a lot of unconstrained aspects to this problem. So what I'm going to do is I'm going to try to state the assumptions that I'm making and see where they lead. It may turn out that some of those assumptions aren't correct, and so the things that are based on those assumptions won't be correct. But I think the appropriate way to proceed when you have a problem that's unconstrained, the least you can do is say what you're assuming and see where that takes you. And the co-authors are Nick Cowan, who's one of yours from a few years ago. He has a 5-year postdoc fellowship at Northwestern, and Fred Chesna, who is on the faculty at University of Chicago. Okay, so this is just sort of an outline of what I'm going to talk about. First, just introduction to weathering and weathering can happen on continents and at the seafloor. Then this is the meat of the talk. Uh-oh. Do you know why that happened, Ty? It didn't like Kibros.
Tyler, we need to reshare the slides on Adobe Connect.
So actually, I think the most important part of this...
Tyler, we lost the slides on Adobe Connect, sorry. Could you reshare?
A couple different limits that are instructive for the behavior of the full model. And that's the part of this that I believe that I would put the most certainty on, at least if you believe the assumptions that I make in the limits that I take. So I think that's something, so pay attention to that. And then this waterworld self-arrest idea, this is where the wild things are in this talk.
We're having issues with the online part. I think
They can't hear me?
No, when it's decided to say exit.
So it quit out. Yeah, so the waterworld self-arrest part That's the more speculative part, and it's sort of an interesting idea, and I'd be interested to hear what anyone thinks about it. Is it on? Okay. I also forgot to mention that the paper describing this work is on my website, if you want to look at that after this. This section, observational prospects, probably I'm going to have to skip, given that it has to be a short seminar. And then just some more general issues about seafloor weathering, the outer edge of the habitable zone. I'll introduce this term seafloor weathering in a second. This last section, so everything up here that I'm going to tell you, I'm not going to show any sensitivity tests, but this is all stuff that is very robust to changes in model parameters. This last section is parts that are not so robust, and the non-robust aspects of them is actually what's interesting. I should probably stop waving this around. It's going to get distracting. And so that's another sort of speculative part, and another aspect of weathering at the seafloor that could be important for habitable zone. Okay, introduction. Everyone probably knows about this. You have a balance maintaining the CO2 in the atmosphere along time scales, the carbon cycle. You have outgassing of CO2 into the atmosphere-ocean system. And you normally have this silicate weathering. I'm not going to spend too much time on this because I think everyone knows this. On the continent that responds to temperature and CO2, so higher temperature, higher CO2, it runs faster, which is a negative feedback.
Sorry, issues.
Having issues. Should I just keep talking?
Yeah, you can keep talking. They can hear you and they can see you walking around, but they can't see the slides is the issue that we're having right now.
Okay, but the new thing, the thing that I'm going to talk about that's not in most habitable zone pictures is weathering that can happen at the seafloor. So I'm going to be trying to take into account weathering that can happen at the seafloor. So removal of CO2 from the ocean atmosphere system happening at the seafloor, where you could have basalt exposed at the mid-ocean ridge, and then you have hydrothermal systems and seawater working into the basalt, reacting with the basalt, carbonizing it, removing carbon from ocean atmosphere system that's eventually buried in a similar way to how the calcium carbonate that's precipitated from continental weathering is buried in the sediment, then eventually into the mantle. And so I'm going to try to add the seafloor weathering into this picture of what sustains the habitable zone, and then see what happens as you change the land fraction and how the habitable zone responds. Okay, so first of all, I just want to say something about the continental weathering.
So, just
keep going.
So I'm going to point the camera at the screen, so just play it as you normally would.
Okay, that's easy. Sounds good to me. Okay, so this is this paper by these French guys, and what they're doing is they're plotting, they look at a bunch of different rivers. Each of these dots is rivers. I'll explain what the different colors of things mean. And what they're doing is they look at the runoff, which is sort of like the total amount of precipitation that hit that river catchment area, and it's the amount of water flowing out in the river. And then they plot the chemical weathering rate, which is, they're plotting basically what we want to know for the continental weathering. And what you can see is there's some sort of reasonable correlation between precipitation or runoff and chemical weathering rate. And then down here, they're doing the same thing with the mean annual temperature. And was it a question? No. And what you can see when they do it as a function of temperature is that there seems to be a correlation, except for these ones where there isn't a correlation.
Is the runoff, is that rainfall?
Yeah, like how much water is coming out in the river. What's the river flow?
Okay, so it's not rainfall, millimeters.
It's integrated integrated over the catchment rainfall. I think that's what
The river output divided by the area of the catchment.
Yeah, I think that's what we're talking about. Yeah, exactly. So average rainfall over the catchment area. Okay, so
Evaporation.
obviously this is supposed to be a function of both these things. So the situation could exist where you have low runoff, and that's what causes it. And even if the temperature is high enough, then you don't have enough runoff to get the value of weathering that you would expect. And so there may be some of that going on, but you also have the Amazon, which has a high runoff, having a below what you would expect a value of chemical weather. And so the point is that there's a bunch of things that can affect this, and it's not sort of a dead-on one-to-one correlation. And if you go in the new update of how to build a habitable planet by Langmuir and Broker, they have a scale where they there's a qualitative ranking of all the theories that they go through. They sort of present the evidence, and then they rank them on a scale of 0 to 10. And so they give the Big Bang Theory a 9.9. They give theory of nuclear synthesis in stars a 10. And they give the silicate-weathering a 6. And that's important because whenever anyone talks about the habitable zone, they're talking about silicate-weathering feedback, and the evidence we have that this is functioning on Earth is only a 6. And that's the lowest value of anything that they're willing to put into their textbook. So this is something, there's still a lot of interesting problems to work on with this. That's what I'm saying. Now, on the other hand, seafloor weathering. Now, this is what I'm talking about when I talk about seafloor weathering. You have some basalt that you took from the ocean basement, and it's got little cracks in it. And into these cracks, there's a hydrothermal circulation, and there's a percolation into them of seawater, and then it reacts with the basalt, and it precipitates out carbonates. And so you can see these veins. So these are considered younger ones, the thinner ones, and the older ones are thicker ones, and they can eventually merge together. And the idea is you can store a huge amount of carbon in the ocean basalt, and then it can get subducted later. And if you look at these reactions in the laboratory, and you crush up a bunch of basalt, and you react it with seawater of different temperatures and different, in this case, they're changing the pH, which corresponds to changing the CO2, you see a strong function of temperature and pH. You see that the reactions show a strong function of temperature and pH. And so, in theory, you could build a negative feedback on climate based on that. You know, the temperature could increase the ocean water temperature, increase the bottom of the ocean temperature, and eventually you could increase seafloor weathering and ameliorate the climate change that would result from that. But the problem is that there are a number of reasons to think that these laboratory changes are not what you're actually going to see if you do this in the real system. And in particular, you had these really crappy correlations when you go measure in the river, but you get the same sort of relationship if you crush up the right types of rocks in the lab. And so there are a lot of complicating factors that can mess this up. And even more so, the surface temperature is a lot different from the temperature that these reactions feel. And in particular, most of these reactions at the seafloor are happening, they're happening maybe 500 meters to a kilometer down into the basalt at 20 to 40 Celsius. And that temperature, what determines that temperature is probably the heat flux from the interior and not the upper boundary condition to that system, which is the temperature at the bottom of the ocean. And so the standard assumption when people consider seafloor weather is to assume that there's no dependence on the surface temperature. And based on these type of laboratory measurements, to assume that, that the dependence on CO2 is weak. And so this is kind of a classic paper on this subject, Caldera 1995. And this just shows, he has a number of these different boxes to simulate different processes, atmosphere-ocean system, and then down to the seafloor weathering. And what he gets out of the model is a dependence of CO2, of seafloor weathering, in this case shown here, and of silicate weathering on land. What you can see is you've got to get the CO2 extremely high to get much changes at all in the seafloor weathering. Okay? So most people who have considered this problem have concluded that seafloor weathering should have very weak or no dependence on surface temperature of the planet and a weak dependence on the CO2 of the planet. And those are the assumptions I'm going to make here. Now it's possible that in certain cases those assumptions could be wrong. It's also possible that those assumptions are wrong on current Earth. So in particular, this type of work is based on 5 to 10 cores down into the basalt. So it's not like there's a huge sample of what's going on down there. But that's what I'm going to assume. Okay. Okay, so I just argued that the weathering could be very different on, like continental weathering and seafloor weathering could behave very differently. But at the same time, we have numerical simulations that suggest that planets in the habitable zone of stars like the sun could have vastly different quantities of water delivered to them, so by orders of magnitude. So you could have planets that end up, very dry right around the habitable zone, or planets that end up very wet. These colors, indicate this is a wet planet, dry planet, it's a log. And then this is Earth, somewhere in this range. So you can have planets 10 to 100 times wetter or 10 to 100 times drier in the habitable zone. And this is also by someone from your program, I believe, Raymond. So at the same time that the weathering of planets could have a strong dependence on how much land you have, we could expect that habitable zone planets could, at least at the delivery level, have vastly different amounts of land exposed. And so what I want to do is I want to try to make a stab at this problem. And I want to see what the effect of changing the land fraction on a planet is in terms of its weathering behavior and width of its habitable zone. And so I'm going to be considering things ranging from waterworld to something with maybe like 90% of the planet covered by land. And I'm not going to be considering a completely land planet. So the complement of what I'm talking about today is this Abbot paper where they talk about a dry planet. And these are some of the assumptions that I'm making. So the first thing is I want a planet that's geologically active. So let's say plate tectonics, to make it simple. Maybe there's something else that works like plate tectonics that can release CO2 and bury carbonates that you create. I don't want a carbon planet, so silicate rocks to get these types of things working. I want a large reservoir of carbon and carbonate rocks, so I can build up large amounts of CO2 if I need to, going further out in the habitable zone. And this is important. When I say water world in this talk, I could mean 1 meter of water above the highest topography. I could mean 10 kilometers of water, 20 kilometers of water. But I definitely don't mean 1,000 kilometers with all kinds of strange ices under pressure at the bottom of the ocean. I'm talking about something that looks like Earth, but maybe has 10 times as much water as Earth does. That's a water world in the context of this talk. This is not that important, and I already talked about this assumption.
Do you assume the planet is alive or not?
Not explicitly anywhere. Not explicitly anywhere.
Does the depth of the ocean matter?
So the depth of the ocean could come into play. For example, if you had, I'm kind of trying to get rid of that as a problem by saying small water fraction. So suppose you had a 200-kilometer deep ocean. You could have so much pressure that it could make the CO2, cut off CO2 outgassing. So you could have effects like that. But I'm not considering those types of planets. So I'm taking something like Earth, and the only thing I want to toggle is the amount of water it happens and that it has on the surface, and I only want to toggle that within maybe an order of magnitude each way. Okay, this is the meat of the talk. So the next maybe 10 slides, if you need to take a nap, wait till after those are done. Pay attention now. So there are going to be some equations. Please don't take a nap yet, because that's actually what is important about this talk. But I tried to put in some diagrams and stuff too. Okay, so now I'm going to tell you about the actual model that I'm using. How am I calculating weathering rates? So I'm basing it on this WAC paper from 1981, the continental weathering. So WL, that's weathering on land. And this is all the dimensionful stuff. And so it's going to depend on precipitation, which I'm going to make a function of pressure. It's going to have some power law dependence on CO2, which I'm calling phi here, and an exponential dependence on temperature based on an Arrhenius type relationship. Seafloor weathering, I'm pulling this from Caldera, is basically going to be a power law dependence on the proton concentration in the ocean. No dependence on temperature. So that's actually important in what's going to come. These are the standard assumptions. The only difference, the only main difference that some people will use is instead of using, making it a function of the proton concentration in the water, they'll make it a function of the total dissolved inorganic carbon. It turns out that when you do that, the only difference when you relate it to CO2 is just changing that exponent. So it will give you a slightly different exponent, but not very much. It's not an important difference. When I combine these, I get this relationship for weathering. So again, this is a zero-dimensional picture of the weathering on the planet. Non-dimensionalized everything. So 1 unit of T wiggle is T. 1 unit of T, no wiggle, is equivalent to TU units of T wiggle of the dimensionful quantity. And then, so this is the seafloor weathering part. The continental weathering part comes in here. This is important. Gamma is the land fraction. I'm making a particular assumption for how the land fraction is going to scale. With how the continental weathering is going to scale with land fraction. This assumption corresponds to just growing a self-similar continent. If you imagine the continent growing in different ways, you might have like a square root dependence. If it's the area, if it's the perimeter rather than the area of the continent, that's important for the seafloor weathering, which it might be if the continent's all broken up. That doesn't end up affecting the results very much. And this data zero term, it says if you put all of your parameters at their standard value, this goes to 1, this goes to 1. If land fraction is equal to the value on current Earth, this goes to 1, this goes to 1. And beta 0 is your estimate for how much seafloor weathering happens as a fraction of the total weathering on current Earth. And our best estimate is that it's about 25% of total weathering on current Earth. But there's an uncertainty of probably roughly 100% in that. So it's probably between 0 and 50%. And then this assumption, if you have a closed system, I'm calling the outgassing gamma the big gamma. Little gamma is land fraction, big gamma is outgassing. It's never going to come back in for the rest of the talk because I'm just going to assume there's some constant outgassing that doesn't depend on where the planet is in the habitable zone or anything else, surface temperature of the planet. I'm just going to set that to a constant. And the constant outgassing has to equal the weathering. So that's how you get a closed system. Okay, so to solve this, you need a weathering. So I need to write down equations that I can solve for temperature and CO2. So I need something for weathering, a weathering relationship, which was big gamma equals the weathering function of phi and t. And then I need some sort of climate model. And so this is my climate model. So any of my friends, I don't think any of them are here, from atmosphere and climate here, would probably take me out back and shoot me for this. But this is my climate model. It's zero-dimensional. And what it is we have incoming solar radiation. We have an albedo that can reflect. And then we have the outgoing infrared emission to space. So I have one equation to take us from the alpha to the omega of climate. What I'm going to do is first I non-dimensionalize my infrared emission to space, and then I expand it. So if I non-dimensionalize this, I just set this to, I non-dimensionalize everything by the current insulation. And so what I'm left with on this side is a quarter 1 minus alpha. And so I expand around that. So in the base climate, I just need to have my outgoing emission to space equal the absorbed radiation. That's what this term means. And then I capture, this is, if I increase the temperature of the planet, I'm going to want to emit more radiation to space. And I capture all of that physics in this one parameter. And if I increase the log of the CO2, I'm going to emit less radiation to space. And I capture all that physics in this one parameter. So I only have 2 parameters for the radiation scheme. I grab those parameters from Ray Pierre-Humbert's climate book, where he uses a radiated convective model and calculates their value. And what I'm left with when I plug this back in is this for the climate model. So I have a simple climate model, and what you should know about it is if I increase the insulation, S value, the amount of radiation that from this star that the planet is hit with, I can deal with that either by increasing temperature by an appropriate amount of units, regulated by this omega-1, or I can deal with it by decreasing the CO2. And so in the standard silicate weathering feedback, you get some combination of both. You increase the insulation, you increase the temperature some, and you decrease the CO2 some, and that's why the temperature didn't increase as much as you thought it might.
What happened to sigma t to the fourth?
Yeah, that's right there. Now it turns out that if you linearize roughly between, let's say, minus 10 Celsius to 40 Celsius, you might think sigma t to the fourth is going to deviate fairly far from linearization, but because of the water vapor feedback, it actually looks, the actual function isn't sigma t to the fourth, it actually looks more linear. So it makes this a better approximation. That's not to say I'm really defending, bottling all of climate into 0 dimensions and doing this, but that's sigma t to the fourth. Okay, this is an important equation. So what I do is I take the model, and what I'm interested in, the most important quantity for the rest of this, is dTdS. So how much the surface temperature of the planet, did I ever explain what those are? I should have put some little things explaining what these are. How much does surface temperature of the planet respond to changes in insolation? So you could get insolation changes because the star is warming up with time, getting more luminous, and you could get insolation changes because you're going further from the star or closer to the star. But what's important for the habitable zone is that this value be as small as it possibly can be. And the limit, if this were 0, then you could just move the planet anywhere you wanted, and the surface temperature wouldn't care. So if you started in the habitable zone, you'd always be in the habitable zone. But we want this to be as small as it possibly can be. And this term right here, this is the climate sensitivity if you don't have any changes in CO2. So every unit of insolation change gets converted into a temperature change. This is the maximum you can get for the climate sensitivity to external forcing. And this term describes any weathering feedbacks. We're going to change the CO2 in order to keep the temperature in a smaller range. So we want that to be low. And after writing down the complicated weathering parameterization, I'm going to simplify it here because the explicit form of those terms doesn't matter for what I'm going to say in the next 2 slides. And so what I'm going to do is I'm going to say the total weathering is equal to some function of the land fraction times the continental weathering, which is a function of CO2 and temperature, plus some function of the land fraction times the ocean weathering, which is a function of CO2 and the temperature. It's pretty hard to cook up parameterization where this gamma function is somehow inside here. So this is a very safe assumption that you can separate these variables out. And all I'm going to require about these functions is that if you have a water world, you can't have any continental weathering. And if you have a land planet, you can't have any seafloor weathering. So I think those are basic safe assumptions. And now is when you should wake up. So these 2 slides that you should pay extra attention to. So most people think that seafloor weathering is independent of surface temperature. That's something that more work should be done on, but that's sort of the null hypothesis right now. That's what people think. And so what I'm going to show here is that if that's true, then a water world can have no climate stabilizing weathering feedback, and therefore is going to have a much smaller habitable zone. So that has direct implications for planets being detected today. And so the way I do that is I take this equation, and I differentiate with respect to S, and we remember that W is equal to a constant, so the ddt of this equation has to be 0. And you just sort of move the terms through, and this is what you get when you differentiate the weathering with respect to S. And I'm going to be considering water world. So F of gamma equals 0 has to equal 0, so this term's gone. And I've constructed, by construction, the seafloor weathering ocean, WO, doesn't depend on temperature. So that's the base assumption. And so this term goes away. And what you're left with is that dpds, changes in CO2 as you change the insulation, have to be 0. And so the physical picture you should have in your mind is if the weathering of the planet can only depend on CO2, you've got a certain outgassing rate, and you're going to have to keep putting out more and more CO2 until you've got your weathering high enough to balance the CO2 that you outgassed. And only then can you stop outgassing CO2. And you'll just build up to some immense high CO2 value. Maybe it's 0.1 bars, maybe it's 10 bars, something high. And it's just going to stay there. It doesn't care. The CO2 doesn't care what you do about where the planet is relative to the star, what the insulation is. And so you can have no weathering feedback. And so that's why you get, physically why you get dpds equals 0. And so what that means is your dTDS, your climate sensitivity to external forcing, is just equal to its maximum value that it can take, as long as there's no positive, I'm assuming there's no positive feedback, weathering feedback. So you just get the maximum possible value. Every unit of S goes into a unit increase of T, and this is the change you get in the habitable zone. So here's the sort of schematic picture of what's going to happen. You go from a planet with some land and a lot of ocean, some sort of relatively wide habitable zone like this, and now all of a sudden, on the water world, these are your habitable zone limits. So it's an order of magnitude smaller. And so all of that follows just from these basic assumptions. The second thing I'm going to consider is I'm going to say, what if seafloor weathering is a constant? What's going to happen to this climate weathering feedback? The reason that I'm considering that limit, there are two reasons. The first is, we saw from the caldera work, the seafloor weathering has a weak dependence on CO2. And it's weak enough that this limit is a pretty good description of the full model, which I'm going to show in a second. So it's an instructive limit to consider. The second reason is there's a possibility that seafloor weathering is actually limited by the circulation of ocean water and hydrothermal vents through the basalt. And if that's the case, then it doesn't really care about the CO2 or temperature at all. So there is a physical limit where this is actually correct. We don't know. Currently, people think that that's not the case, but it's possible that that's the case. Okay, so what happens in this limit? So I said that the seafloor weathering is constant, so that knocks these terms out. And then, right away, because I assumed that the land fraction function was separable, which is a safe assumption, you're left with this, and so you can solve for dpds and plug it into dTDS, and you get something that has no dependence on gamma. So there's just no dependence on the land fraction left. And what this means is, so if you go to a planet with more land to a planet with less land, you've got, if the land weathering is the dominant term, and you go to a planet with less land, you're going to get a higher CO2, and you're going to get a higher temperature. But you're not going to get a higher change in temperature as you change the insulation. So you'll get a small shifting in where the habitable zone exists. So it's going to shift outwards a bit, but the width is going to stay the same. And so this is a relationship that holds up in the full model. So the basic picture that you can construct just from the simple examples is that a water world should have a very narrow habitable zone, and planets that have some land should show a weak dependence of their habitable zone on the land fraction, which is a powerful result because what it means is that the previous habitable zone theory should be robust in these cases, which has been derived without any explicit reference to what the land fraction is. Okay, more meat. This is the full model results. So I'm not considering my simple limits anymore. I've gone back to the complete model. And what I'm showing here is, imagine the evolution of a planet like Earth. These are different land fractions as a function of insulation. And here I've just plotted for a star like the sun what time these would be. These are my non-dimensional variables, and here I've turned them back into physical units. Excuse me, log CO2 in bars, and this is the temperature. And I've just sort of drawn kind of rough habitable zone limits where a moist greenhouse might be where a snowball might be. This is some other people's idea that I don't think is all that useful, of where photosynthesis might shut off, because there could be other types of life that don't need, there are other types of life that don't need photosynthesis. And what you can see is, as you increase the insulation, so you're going, your planet is, the star is aging, or you're going closer to the star, you get increases in temperature, but they're ameliorated by the fact that the CO2 is decreasing. And so that's the silicate-weathering feedback. And as we increase land fraction like this, you get higher temperatures, but you still get a dTdS, this slope, that's about the same. And so your habitable zone is just shifting rather than shrinking or expanding. Now, if we plot on top of that a planet where we set the land fraction to 0, and you can no longer do any land weathering, you get a much more rapid increase into the moist greenhouse. And the reason is, this is what I was describing before, the CO2 just builds up until it's high enough to balance the outgassing, so that the weathering gets high enough to balance the outgassing, and sticks at that high value. In this case, it's like 6 bars or 7 bars of CO2. And so you just rapidly go into the moist greenhouse state. And so what that means is you get a much narrower habitable zone. Okay. So I just want to say something about why that's happening in the model. Basically, what I'm plotting here, forget about what B is the scaling of CO2 in the WAC parameterization. The point is, you get a similar picture at both of these potential values of B, which might be different because of the effect of land plants. But the idea is, this is the insulation level, modern, higher, lower. This is the land fraction, so this is 10%, 1%, 100%. And you can see there are these broad regions where dTdS, this climate sensitivity to external forcing parameter, is roughly constant in both cases. And they tend to happen when the planet is warmer. And the planet might be warmer because you make the land fraction smaller, or it might be warmer just because you increase the insulation. And so why does that happen? Well, we can write down in the full model what dTdS is. It's this value you get with no weathering feedback times something that's always between 0 and 1, which describes the weathering feedback. If there's no seafloor weathering, then this term equals 0, and you get sort of this term describes the land weathering feedback. And this kind of annoying term is the one that comes in from the seafloor weathering. But what you can see, and this is critical, is there's this e to the minus t. And so anything that gets temperature more than 10 degrees, 20 degrees warmer than today is going to kill this term, even if it's just 10 degrees. You get this term totally killed, and you end up in a limit where dTdS is just equal to this constant. And that actually is a very good description of all of those planets broadly. And so this is an explanation of mathematically of why in the model you get those constant dTdSs and those wide habitable zones for such large land fraction range. Okay, this is the part of the talk where the wild things are. So this is the more speculative stuff. I'd be interested in your comments on it. So I just said that, I just made an argument that a water world is not going to be an attractive place to look for life, other than the problems biologists might have, that it's not going to be a place with a wide habitable zone. And so now I'm going to talk about something that might be able to save water worlds, potentially. And so the idea is, if the water world gets such a high CO2 that it puts itself into a moist greenhouse state, and their water in the stratosphere is being broken apart and hydrogen is escaping, and you're losing oceans of water. What if you reach a point, as you decrease your water level, where you start to expose some sort of land? It might be basalt, it doesn't really matter what it is. And then you can engage these land weathering feedbacks that are a strong function of temperature and are going to be extremely rapid if you're in a moist greenhouse state. Is it possible that you could decrease the CO2 fast enough to arrest this water loss while you still have a partially exposed land and some amount of ocean? So there's some T0, the time it takes to initially expose the continent. That's going to depend on how much water there is in the planet. And for some very moist water world planets, that T0 is going to be essentially infinitely large. It's going to be millions of years, and we don't care about it. But for a planet where that T0 is small enough and you eventually expose continent, it's going to take, the time scale for this water loss to occur. It depends on a lot of parameters. For example, it's going to probably be longer on a super Earth. But for a planet like Earth, 100 million years is a good time scale to keep in mind. Whereas the weathering feedbacks, we have reason to believe that they happen more like on a scale of 10 million years. And there are some things that could mess this up and make it take longer. But it's reasonable to believe that at least some planets, you could have a short time scale to draw down CO2. And for example, we have in Earth's history the snowball Earth, where we think the CO2 was built up to immense values, maybe a tenth of a bar of CO2. And on a very short time scale, 10,000 years, 100,000 years after the snowball Earth event, all of that CO2 was able to be drawn out of the atmosphere through weathering. So it could be, in fact, a very short time scale. But it's definitely reasonable that it's under 10 million years. So what the combination of these means is it looks like it's at least plausible that you could have a situation that you're losing water in a moist greenhouse, you expose some type of continent or land, and that stops the water loss because you engage weathering, land weathering. And so it's a mechanism that water worlds could turn into planets that have a more robust weathering feedback and a wider habitable zone. And the way it would look in that diagram again, insolation, temperature, is you're cooking along as a moist greenhouse. You're cooking along as a water world. You hit the moist greenhouse, and then on a geologically very short time scale, you go through that, but stop it as it's happening, and then you go through as a planet that has 30%, 50%, it doesn't really matter, water that has a wide habitable zone. So it's a way that the water world can save itself. Running out of time. So I'm going to skip this observational stuff. I can talk about it later if anyone wants to. I just want to make one quick point. This is what it means. This is the bottom line. If the stuff I'm saying is correct and you're an astronomer, this is what it means to you. Point one. And I'm assuming that you're Bill and Ted, if you're an astronomer. So if you think the planet has some sort of land fraction, then you're happy. It doesn't matter how much. You've got a wide habitable zone. The previous scalings derived for where the habitable zone is should be roughly right. If you think you're dealing with a water world, then you're not happy, because it should have a very narrow habitable zone. And things that you find that you might think are in the habitable zone are unlikely to be actually there. Your guy, Nick Cowan, has some work on how you could estimate land fraction. I'm not going to go into that. And then I have to skip these ones. And I just want to make a couple brief points about seafloor weathering and the outer edge of the habitable zone. And then I'll go to questions. So I'm going to do it in like 2 more minutes. Okay, so everything I told you before was robust when I changed things in the model. Now I'm going to tell you something that's not robust. So this was what my seafloor weathering parameterization looked like. There was some constant, and then there was some exponential power of CO2, of feet. Okay, so we can imagine a situation. How can we get the most possible? The seafloor weathering can impose a limit on the CO2 that the planet can attain. And the way you can imagine this happening is, imagine you start going to a lower and lower insulation, so low that the temperature and CO2 dependencies of the land weathering just shut land weathering off. There's no longer any land weathering. And now you have to balance all of your outgassing with seafloor weathering. And if you have a strong dependence on CO2, you won't need to increase the CO2 very much to do that. And if you have a weak dependence on CO2, you'll have to crank the CO2 way up, and you'll have not very much of a limit on the CO2 you can get. But it turns out that it's exquisitely highly dependent on what value you choose for n. So for example, I chose n of 1/3, which corresponds to what Caldera did. If you change n to point, and when I did that, the maximum CO2 I could build up on my planet was like 7 bars. If I change that to 0.5, which is totally within the error bars, all of a sudden I can only get 1/10 of a bar of CO2 before seafloor weathering chokes you off. And that's critical because if you look at the outer edge of the habitable zone, so for example in this Gliese 581 system, I'm not plotting the planet that nobody knows if it's there or not, but I'm plotting only planets that we think are there. There is this planet, I don't think anyone argues with that, this D planet, that's somewhere near the outer edge of the habitable zone. GCM calculations suggest you need something like 10 bars to make this planet habitable of CO2. Well, if seafloor weathering limits you so that you can only generate 1/10 of a bar, then you're not going to be able to keep that guy habitable, at least with the classic mechanism of just increasing the CO2. So that's why this is important. And there, so, I'm gonna wrap up, but basically, Kleep and Zonley have made similar arguments for early Earth, and they find that if you have a stronger relationship of seafloor weathering on CO2, it gets a lot harder to keep to get the CO2 high on early Earth, faint young sun problem. And Guillaume Lehier considered this problem for the snowball, and he actually found that seafloor weathering in his model was so high that he could only get a couple tenths of a bar of CO2, and that was potentially a problem for escaping from the snowball. So there's clearly some uncertainty in terms of these seafloor weathering parameterizations. But suppose we find out that it's strong, that there's a strong dependence on CO2. This could really kill the outer edge of the habitable zone. I'm going to skip this one and that one. Okay, so this is the last slide. So these are the take-home messages. The first is that a planet that has some sort of land fraction, something between a few percent and 90% or something like that, we should have a robust, wide habitable zone if previous habitable zone theory is correct, of course. If the silicate weathering idea is correct, we should have a robust, wide habitable zone that could shift around a little based on the land fraction. And if you're doing more than a zero-dimensional model, based on how these continents break up, but it shouldn't show a strong dependence. However, if what we think we know about seafloor weathering and continental weathering is correct, we can show with a simple mathematical model, we can show that implies that a water world is going to have no weathering feedback and a very narrow habitable zone. So those are the take-home messages. And if you enjoyed this, I have another talk on snowball Earths on Thursday. I don't know where this building is, but wherever JHN is. So thank you for your time.
Thank you, Dorian, for persevering through all of our technical issues. So we have time for a couple questions. Yeah.
Are there scenarios where seafloor weathering doesn't happen? I mean, like worlds where you have sediments that completely cover everything and it's just dead? I mean, it's a surface phenomenon, right? I mean,
Yeah, you have to be able to get the hydrothermal circulations through the salt.
yeah, but say if you don't, I mean, there are those situations where you put,
Yeah, I mean, if
with those sediments,
yeah, if you really have, well, so I'm sure the answer is yes. I'm sure you could construct examples, but at least on Earth, a lot of this important seafloor weathering is happening near the mid-ocean ridge, where there's not much sediment. And then eventually it's getting covered with sediment, and there's probably less action happening for the last 20, 30, 40 million years as it gets dragged over and subducted.
it's like Mars.
There's no ocean.
If you put an ocean on Mars, geological activity is 100 times less.
Well, so yeah, one of my initial assumptions, of course, was that it was geologically active. So if you don't have CO2 being outgassed, if you don't have geological activity, you also don't have CO2 being outgassed, right? So it's not clear any of these habitable zone ideas are going to work in that case.
So in the Abbot paper on dry papers, they got to have a zone to expand in both directions.
Yeah.
So, and here, when you're going from a small amount of land, you get to have a zone just to move out. So presumably, at some point, you get to a small enough or a large enough fraction of land that then you kind of get to the Abbot limit. So Did you sort of explore when that happened? Like, what?
Yeah, I glossed over the difference between this and Abe, but actually a very important point is my climate model is a little rinky-dinky, and Abe et al. Put all of their effort into their climate model. So first they run a really fancy GCM for the outer edge, then they work really hard on a radiative convective model for the inner edge. But they never actually do any explicit calculations of weather, where I put all my effort. So we're actually kind of looking at different aspects of the problem, other than the different land and ocean fraction. We're looking at different aspects of the problem. They're considering how the climate, without any weathering feedback, how it happens. I'm considering the weathering feedback.
And so you never got any of your cases to expand the habitable zone at the inner edge as you've changed land direction?
No.
Okay.
I didn't, no.
I have a question from the online crowd.
So Jacob Hockmeistra has a comment.
Yeah.
Adam Edson has performed calculations of tidally locked Earth-like planets orbiting low-mass stars.
Yeah.
He used Earth-like geography and found that the atmospheric CO2 strongly depends on whether the substellar point is beneath water or land.
Yeah.
This was published this year. It seems consistent.
Yeah, exactly. Okay, so that's in the class. So I assume 0 dimensions. So I can't consider a problem like that. What he's saying is, if I move, essentially it's a two-dimensional issue, whether I move my continents under the sun or out of the sun. And a related issue is how I break my continents up. And all of those things could definitely have effects. And in a case where you have a huge asymmetry in the forcing, where you have all of your insulation on one side and not on the other, then you would expect spatial heterogeneity to be more important. And this is an example of that, where you're going to draw down the CO2 if you put the land underneath.
Okay, a few quick announcements. So next week we have Boswell Wing who's going to be speaking. He's on sabbatical here. We're not broadcasting that talk for the people joining us online. In 2 weeks, please join us for Professor David Brain, who's going to be talking about whether or not planetary magnetic fields matter for planetary habitability. That is going to be broadcast, so I hope our online people join us for that. Almwa's general exam immediately follows this. I'm going to be taking Dorian out to dinner tonight. And if you're interested in joining, please come speak to myself or maybe Vicki, because I'm going to have to jump out here, so maybe she can help with organizing. So with that, let's thank Dorian one more time.